All right, here we go. For me, this is my final question to film. For you, this is probably your first question to watch. This is question number 1 from the 2018 AP Calculus exam. So if you were a senior in May 2018, this would have been your very first question that you'd see when you open that exam booklet. It is calculator active, so make sure you get your calculator out. And let's go. People enter a line for an escalator at a rate modeled by the function r, given by r of t equals 44, t over 100 cubed, times the quantity 1 minus t over 300 to the 7th power for the time interval 0 less than or equal to t less than or equal to 300, and then 0 for t greater than 300. Let's think about that for a second. People enter a line for an escalator, so we're entering a line for an escalator at a rate modeled by this function below. From 0 to 300, we have a rate, and that rate is some function. And as soon as time is greater than 300, 0, meaning there's no more people, or that people are getting on the escalator at a rate of 0. R of t is measured in people per second. T is measured in seconds. These units are all probably going to be important. As people get on the escalator, they then exit the line at a constant rate of 0.7 persons per second. And there are 20 people in the line at time t equals 0. So already we've got a whole lot going on. I don't even want to look at parts A, B, C, and D yet. I want to make sure that we understand what's going on. We've got an escalator, so one of those like moving staircases, right? And R of t is how quickly people get onto the escalator, and then they go up, 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 up. And then you've got this other rate they get off at a rate of 0.7 people per second. And at time t equals 0, we have 20 people in line. Yeah, okay. So this is one of those classic in and out problems. It's a rate functions question. We have people getting into a line for an escalator. We have people getting off the line. Like, I guess that means that they're actually getting onto the escalator at a particular rate. We've got all these things going on, and we know that we start off with 20 people in line at time t equals 0. All right, let's see what we can do with this. What kinds of stuff are they asking? In part A, how many people enter the line for the escalator during the time interval 0 to 300? Our function r of t is the rate of how quickly they get onto the line, and so they want to know how many people enter the line on the time interval 0 to 300. So r of t is a rate. You want to know it's a how fast something's happening. You want to know how many people actually get onto the line. So we're going to integrate. We're going to integrate the function r of t from 0 to 300, because r of t is how fast people are getting onto the line for the escalator. And if I integrate that rate function, it's going to give me a total. It will tell me how many people. So we're going to use the calculator. We've got a very ugly function over here, but fortunately we have the graphing calculator. So I do not want you to actually try to integrate this by hand. Instead, let's go to the calculator. Okay. On my calculator, oh, this is unfortunate. Okay, I'm going to focus on there. Sorry. So on my calculator, I have typed in the function f1 of x equals 44 times x over 100 cubed times 1 minus x over 300 to the 7th power. When I first graphed it in my normal viewing window, I just see this horizontal line. So I know something's wrong. I need to remember that there's a domain restriction here of 0 to 300. So I'm going to go over to menu. I'm going to change my window. My window settings, I'm going to start with an x-min of 0 and an x-max of 300. I'm going to leave the y-min and the y-max alone right now. And this is what my function looks like. This is the rate function for how fast people enter the line to be on the escalator from 0 to 300. Great. I'm going to go on over to my calculate screen like I've done before. And I'm going to do menu, calculus, numerical integral. We integrate from 0 to 300. The function is f1 of x. And I'm getting 270. What that 270 represents is the number of people that have entered the line in those first 300 seconds. So let's go back over to my notes. Here we go. This tells me that the integral from 0 to 300 of r of t with respect to t is 270. This is 270 people. If you're curious about the units, that's it. That's your answer. The College Board awarded 1 point for knowing to set up the integral, another point for coming up with the answer, whether you had the units or not, and so you would have earned 2 points on this one. Pretty standard rate function question, at least at the beginning. Let's see what they've got in store for us in Part B. During the time interval 0 to 300, there are always people in line for the escalator. Okay, how many people are in line at time t equals 300? So at time t equals 300, how many people are in line? I'm going to define this new function r of t to be the number of people in line at time t. So what I want is big R of 300. Well, how am I going to figure out the number of people in line at time t equals 300? I've got to take into account a couple of different things here. At time 300, well, what's happened? We have the 20 people that were in line in the beginning, plus I've got this integral from 0 to 300 of r of t dt. The 20 is the number of people in line in the beginning. This integral tells me how many people entered the line. We already have that numerical value. And before you think, great, I've got it, there's one more thing that's happening. People are getting out of line because they're getting onto your escalator. They're getting onto the escalator at a rate of 0.7 people per second. So what I'm going to do is I'm going to subtract 0.7 people per second for 300 seconds. The 20 is the initial number of people in line. This tells me how many people entered the line. This tells me how many people exited the line because they actually made it onto the escalator. We're going to go back over to the calculator. And it's 20 plus, I want to use this calculation again, minus 0.7 times 300. And that's going to give me 80. So let's go back. We've got 80 people. This is also worth 2 points. They awarded the point for doing this calculation over here. They said that this was the considering rate out, the rate that people are coming out of the line, and then 1 point for the answer. I'm a little surprised that they didn't offer a point for using the initial condition. That's something that I would have expected, but they decided not to do that this time, and well, they're the College Board. They get to make these choices. So that's worth 2 points. Not bad, pretty typical. This is what I would expect. All right, part C. In part C, for t greater than 300, what is the first time t that there are no people in line for the escalator? Let's think about that for a second. I'm looking for big R of t to be equal to 0. Well, what has to happen there? I know that at time 0, we had 20 people in line. I know after 300 seconds, we have 80 people in line, but I also know if I go back to my original function, that starting at 300 seconds, just after that 300 seconds, no more people are getting into the line. So it's only a matter of the people coming off the line. So a lot of ways we can think about this. What I know is that at t equals 300, r of 300 equals 80. There are 80 people in line. What happens is those people get onto the escalator, they get out of the line at a rate of 0.7 people per second. If I take 80 and I divide it by 0.7, 80 divided by 0.7, I can go back over to my calculator, 80 divided by 0.7 is 114.285. Now let's be careful. This is 114.285 seconds. But what is that 114.285? That's how much time after the initial 300 seconds it's going to take for those 80 people to get onto the escalator at a rate of 0.7 people per second. So what I would have to say is it's going to be at t equals 300 plus 114.285, which is 414.285 seconds. That would be the acceptable answer, or if you rounded, 414.286. That guy right there, College Board awarded 1 point. There wasn't a lot of calculus that needed to be done in Part C. It was more about, do you really understand the situation? We had 80 people still waiting to get in line. They get in line at a rate of 0.7 people per second. 80 divided by 0.7 is how many seconds it'll take to get all 80 of those people onto the escalator, but we had to add that to the initial 300 seconds that we required in order to get people on. Okay, doing well so far. Here comes Part D. In Part D, for 0 less than or equal to t, less than or equal to 300, at what time t is the number of people in line a minimum? To the nearest whole number, find the number of people in line at this time, justify your answer. They didn't use the phrase, but they're implying it. I want to know when the number of people in line is a minimum. What this means is absolute minimum. And you'll see in one of the questions later, another absolute extrema question. I don't remember if it's absolute max or absolute min, but this is going to be a little tricky because we need to figure out an absolute minimum. Quick little refresher here. If I look at a graph, and my graph maybe looks like this, I've got some time interval. Let's say here's t equals 0. Let's say here's t equals 300. I can see that I have a local minimum, or depending on what your calculus teacher uses, a relative minimum right over here. And depending on the graph, this endpoint could be lower than this local minimum. Now, it certainly looks a little bit taller, but if I extended this boundary out a little bit more, it could be that the endpoint is lower than the local minimum. The way that we go about doing this is we are always going to look for internal candidates for our local minimum, and then we're going to look at endpoints. One of the things we would have studied back in Chapter 4 is that when you're looking for an absolute minimum or an absolute maximum, you look at your internal candidates. That's where your derivative is equal to 0, or where there's a change from decreasing to increasing. And then we examine the endpoints. All of that comes together to solve this problem. So, what's going on here? I want to go back to the graph. let's go back to the graph. Right now I'm looking at the graph of one function. This is the rate at which people enter the escalator. What I want to do is I want to add on the other rate, which is the rate that people actually like come offline. They get to enter the escalator. Come on. Sorry about that. There we go. 0.7. So let me move this guy out of the way. Let me move this guy out of the way. What happens at first, remember the blue is how quickly people enter the line. The red is how quickly people come off of the line. Before the intersection point, from t equals 0 until this first intersection point, what happens is people get off the line at a rate that is faster than the rate that they're getting onto the line. And so what that means is from time 0 until this first intersection point, whatever it is, the number of people in line is going to decrease. On this next interval, I can see that the blue graph is taller than the red graph. That means people enter the line at a rate that is greater than the rate that they get off of the line. The length of the line, the number of people on the line, grows. It starts at this first intersection point and goes till the second intersection point. And then finally, from the second intersection point on to the very end, I can see that the red line is taller, it's higher than the blue graph is, so the number of people in line is going to decrease. So let's actually figure out where these points are. I'm going to do menu, analyze graph, intersection, a little to the left, a little to the right. The first intersection point, 33.013. Menu, analyze graph, intersection, a little to the left, a little to the right, 166.575. Yep, just want to confirm that those are the right values. I'm going to recreate this graph on my paper so we can continue the conversation. So, give me just a second. Okay, and one more thing that we're going to do while we're here, these values, 33.013 and the 166.575, because these are our internal candidates, I'm going to store those values. So to store, you're going to go to var, store var. I'm going to call this first one A. For the next one, I'm going to go to vars, store var, call it B. I can see that they're now in bold, which means that the calculator recognizes these as values that have been saved. Okay. So from t equals 0 to what I'm calling t equals A, the number of people in line is decreasing because the rate that people leave the line is greater than the rate that people enter the line. On this next interval, when I'm in between, we're going to be increasing, and then we're going to be decreasing on that interval. Okay, we've got a whole lot going on, but we're almost there. Your internal candidate for a absolute minimum is going to be where your local minimum occurs. In order for the graph of R of t, the number of people in line, to have a local minimum, the number of people has to change from decreasing to increasing. Where does that happen? Where is the graph of R of t going to change from decreasing to increasing? Right here. R of t changes decreasing to increasing at t is approximately 33.013, which I'm going to call A. That's my internal candidate. What I need to do now is I need to evaluate r of t at 3 different values. I need to evaluate at time 0 because that's the start of my interval. I need to evaluate at time 300 because that's the end of my interval. And I need to evaluate at time t equals a. We've already calculated some of these before. At time 0, how many people are in line? 20. At time 300, how many people are in line? We already did that calculation earlier in part B. That's 80. What we need to do is figure out how many people are in line at time t equals a. That's my initial 20 plus the integral from 0 to a of little r of t dt minus those 0.7 people every second for a seconds. It's this last one that I need to get on my calculator. So one more time, let's go back to the calculator. We're going to go to the graph. 20 plus the integral, so menu, calculus, integral, from 0, and because I stored that value, I'm going to call it a, f1 of x, dx, minus 0. Sorry about that, minus 0.7 times my a value. And what I'm getting is 3.803. Let's write that value down in our table. Let's come back to the table so we can wrap this up. At my endpoints, I have 20 people and 80 people. At my internal candidate, I have 3.803 people in line. So where is the absolute minimum? What's the smallest number of people that I'm going to have in line? That's going to be this 3.803. But be careful. Go back to the question. Check out that question. The question was, for that time interval, at what time t is the number of people in line a minimum? We know that. That's the 33.013. And then to the nearest whole number, find the number of people in line at this time. So I would say this. The number of people in line is a minimum at t equals a. And because I already wrote down in my paper what a is, it's okay, but I'll write it again. 33.013 seconds. The minimum number of people in line. Now I want that r value is not 3.803. You've done so much work. Don't blow it now. Round it to the nearest whole number. 4 people. That's a long one. These absolute extrema questions are always really, really long. Okay, so the scoring rubric is a little different from the way that I went about doing this, but the way I went about doing this is pretty standard. This is the way that we teach it in the AP Calculus class. So I'm going to say that there is 1 point for the identification of 33.013. College Board and I agree on that. There is 1 point for these answers that we determined, the number of people at each of the endpoints, the number of people at time A. There's 1 point for your final answer, and then there's a 4th point where they say it's for considering. What they write is that where r of t minus 0.7 is equal to 0. That's where they offer a 4th point. We didn't actually do this step. We did it instead by looking at the graph and seeing where does the big graph change from decreasing to increasing. So somewhere in here, the College Board has a way of awarding that 4th point. What I know for sure is that this work would give you 100% of the points if it was presented on the, as your sample on the AP exam. All right, good luck. I know that part D was really long. These questions always are, but that's why they're also offering a whopping 4 points for part D. Of course, in the middle of the test, you will never know that it's a 4-pointer. Hope that was helpful, and I wish you all the best.